Think about what you're made of for a minute. Buildings are made from bricks, steel, glass, and wood. Living things are made from chemical compounds. But all of those compounds are made primarily of only 5 elements. The first task of an architect or an engineer is to understand the materials that he or she has to work with to build. The first job of a biologist, then, is to understand what living things are made of. And that requires us to venture into the world of organic chemistry. So get your papers ready, guys, for a great little trip. Remember, wide right, skinny left. Write your notes on the right-hand side however you want to. See you on the next slide. First, though, we need to have a quick little review of some stuff you should already know. The word atom comes from the word atomos, which means unable to be cut. An atom is a pure element, like hydrogen or gold. They're found on the periodic table of elements. It cannot be separated into any other substances, unlike water, which can be separated into hydrogen and oxygen. So water is not an element, but hydrogen is and oxygen is. All matter is composed of atoms. We know that. Even cells are composed of atoms. And atoms have 3 main parts. Protons are the positively charged particles that you see here in the red in the picture. Protons have a positive charge. They're found in the nucleus. And protons have a mass of 1 atomic mass unit each. Neutrons are no charge. They're neutral. They're like Switzerland. They don't take sides. Neutrons are also found in the nucleus, and they also have a mass of 1 atomic mass unit each, but they don't have a charge. Lastly, we have electrons. Electrons are negatively charged, and they're found outside of the nucleus. They are extremely tiny. They have practically no mass. It takes close to 2,000 electrons to equal the mass of 1 proton or 1 neutron. So they're really, really, really tiny. It would be like weighing yourself before and after you cut your fingernails. Yeah, not a whole lot of difference there. Another acronym to remember, too, that's going to help you when we go through this unit is APEMAN. And APEMAN helps us to remember about the neutrons and the protons and the electrons. And it goes like this. APE. The atomic number of an atom or an element is equal to the protons, which equals the electrons in a balanced atom. So protons are positive, electrons are negative, and they cancel each other out in a balanced atom. So APEMAN, APE, atomic number equals protons, which equals electrons. MAN, the mass number, okay, the atomic mass is the atomic number, which is protons, plus neutrons. So APEMAN. That'll come into play in the ionic covalent bond lab we're doing. Now, as we said, elements are pure substances with only 1 kind of atom. There are about 24 to 26 commonly occurring elements, but there are over 100 known elements. Many of these exist in only trace amounts in the crust or the atmosphere, and some exist only in laboratories. Every element is represented on the periodic table also by a 1 or a 2-letter symbol. And each element has a unique atomic number that equals the number of protons. So for every single element, their atomic number is equal to the number of protons, and that is unique. No other element has that number of protons. So if you think about fairy tale people like Midas and Rumpelstiltskin who turned straw into gold, can't do that because you have to change protons, and protons don't ever change. Now, another type of variation of element that we're going to talk about is isotopes. Isotopes come from the Greek word meaning same and place. So isotopes are different numbers of neutrons, but the same number of protons. So it's a variation of an element. Okay, remember protons always stay the same, but they can have different numbers of neutrons. A common isotope is carbon-14. Carbon normally has 6 protons and 6 neutrons. That's carbon-12 over on the left. Carbon can have 6 protons and 7 neutrons, and it's called carbon-13. Carbon-14 has 6 protons and 8 neutrons. It's very, very unstable, but it's useful. It is found in every living thing in certain amounts and has a very predictable rate of decay. So when you hear of scientists doing carbon dating, what they're doing is they're measuring the amount of carbon-14 in an artifact. And they're trying to guess or trying to estimate how old it is, not guess. So isotopes of the same element have the same chemical properties because they have the same number of electrons. But because they have different numbers of neutrons, they have different rates of decay. And sometimes they're radioactive. This property of radioactivity is very, very useful because scientists can use that to date artifacts, to kill cancer cells, they kill bacteria, and they can even trace the movements of substances in organisms with radioactive stuff. Pretty cool. Back in the 1800s, Dmitry Ivanovich Mendeleev developed this table that sorted the known elements at the time into families, or vertical columns, that all possessed similar characteristics. His table also had periods, or horizontal rows, in which the characteristics of the elements either increased or decreased in a predictable pattern. Now, over the years, this table's been revised, but the basic design still works. 150 years later, that's pretty amazing. If you look at the table, common substances like water and carbon dioxide are not there because, as we said earlier, they're not elements. But I do see hydrogen and carbon and oxygen. You'll talk more about these in chemistry next year, but for now, we just kind of need to marvel at how awesome Mendeleev was. The other thing that's pretty cool is he left blanks for elements that weren't discovered yet at the time, and he even described their properties and said they're going to look like this or behave like this. And you know what? He was right. He was one amazing dude. In biology class, we're going to talk a lot about chemical compounds. And if you remember from prior science classes, a chemical compound is formed by the chemical joining of 2 or more elements in very definite proportions. They can be simple or they can be complex. If you take a look at this diagram, we see examples of molecules. But not all of these are compounds. In the top row, remember molecules are 2 or more atoms joined chemically together. In the top row we see hydrogen, oxygen, nitrogen, and chlorine molecules, but they're not compounds because they're single elements. Okay? The bottom row though does have compounds. Nitrogen oxide, water, nitrogen dioxide, and carbon dioxide. Those are all compounds, and they're very simple ones. Here's a couple of complex ones. These are my 2 favorite complex chemicals. Compounds also have physical and chemical properties that are very different from the chemicals or from the elements that make them up. A good example is salt, sodium chloride. Sodium is extremely explosive in the presence of water. Chlorine, on the other hand, is a poisonous gas. Well, when you get salt in your mouth does not burst into flames and you don't die. So very different chemical properties and very different physical properties than the elements that make it up. Next, we're going to talk about bonding. No, I'm not getting mushy on you. We're going to talk about chemical bonding. Remember, we said a compound is 2 or more elements combined chemically. They bond. Those elements bond. There are 2 main types of bonds that occur, and that's what we're going to talk about in this slide as well as in our Skittles lab. The first type of bond is the sharing of toys. No, actually, it's the sharing of electrons between atoms. This is called covalent bonding. Co means together, and valent has to do with valence electrons, or the electrons in the outermost shell. Just like kids in the cartoon, all of them are happy sharing the toys. So atoms are happy when they share electrons, so they each think that their outer shell is full. The other type of bonding is called ionic bonding. And this happens when certain atoms that have 1 or 2 electrons in their outermost shell give them up or transfer them to another atom that needs only 1 or 2 to complete their outermost shell. Remember from your vocabulary that an ion is a charged particle, positive or negative. It becomes charged when it loses or gains electrons. And this happens a lot. One example is static electricity. So in this cartoon, you see the positively charged ions attracted to the negatively charged ions like little magnets. This is called an ionic bond. And here is what each type of bonding looks like at the atomic level. And this is what you're going to see in the Skittles lab. In covalent bonding, hydrogen has just 1 electron. It really doesn't want to give it up, but it will share it. And hydrogen only needs 2 in its outermost shell to be happy. Carbon needs 8 to be happy. Carbon has 4 valence electrons, so 4 hydrogens can share with the 4 in carbon to make methane. And we see sharing in with nitrogen to make ammonia, and we see it sharing with oxygen to make water. In ionic bonding, the electrons are transferred. Calcium only has 2 electrons in its outermost shell. It would want 8 to be happy. And it's easier to give up 2 electrons than it is to gain 6, so it'll give up 2 electrons. This gives calcium a 2+ charge then, or a positive charge, because it has 2 more protons than electrons. Chlorine nearby has 7 electrons in its outermost shell. So 2 chlorines each pick up an electron. They now have a 1+ charge, a 1- charge, because they each picked up an electron. And they're attracted to this positively charged particle, this positively charged calcium, like a little magnet. So covalent shares, ionic transfers. Covalent bonds also cause attractions between molecules inside of an organism and whatever surface it might be standing on. This is called van der Waals forces, named after the scientist who discovered them, obviously. You can read a little bit more about them in your textbook. What's important for you to remember about van der Waals forces is that they're caused by an uneven sharing of electrons in a covalent bond, and they allow organisms like geckos or flies to walk up walls and actually even walk on ceilings without falling off. Pretty cool. So you've written your notes. Now it's time for the summary and the questions. Remember, the summary goes at the end. 3 or 4 sentences. Tell me what these notes are about. Then either use your textbook or get with a study buddy and come up with your 6 questions. Remember, 3 level 1, 2 level 2, and 1 level 3 question. You can have more than 6 if you want, but you can't have less than 6. So just go do it, guys. See you in class.